Everyone, thank you for coming to my talk. I am Federico Bianchi. I am a senior ML scientist at TogetherAI. And today I'm going to be talking about building agents from the ground up. So a bit of context about me. As I said, I'm an ML engineer. I'm an ML scientist. I'm mainly working on training agents and post-training at Together. My previous experience was as an AI engineer at OpenEvidence, and before that, I was a postdoc at Stanford doing mainly research. So I have a couple of things published. The latest thing is the one I'm showing at the bottom is TextGrad, which is a prompt optimization tool that has been recently published by Nature. I have quite a few packages in the open source, and I'm excited to chat about this if people are interested. So yeah, this is a bit about me. And today's talk is going to be about different things. I also want to mention a conference we are organizing with Stanford and TogetherAI. This was the first academic conference in which both the writers of the papers and the reviewers were AI. So we have this conference in which the first authors of papers are actually AI agents. We received around 300 submissions. We sent out a notification yesterday, and we have around 40 accepted papers. I think this is an exciting event for agents because it allows us to explore which are the limitations of AI in scientific discovery. We have a fully transparent mechanism, so we're going to release everything from the papers to the reviews. And finally, we believe this is going to be a way for us to identify which are the norms that we need to have for AI in science. The idea being we know that agents can do a lot of cool work for us, even in science, but we need to understand which are the possible limitations, which are the things that we need to control, and so on and so forth. So today I'm going to cover 4 main topics, and these are first deconstructing agents. So I want to talk a bit about the definition of agent and break it down a bit and start from that. I'm going to then mention how we build some agents using the React framework. I am going to talk a bit about supervised fine-tuning in the context of learning new agentic behaviors. And finally, I am going to mention how we can use reinforcement learning to even improve those behaviors again. Some more information about this talk. So when I was planning this talk, I thought it was fun to somehow share a few of the things I've been doing over the last few months, some of the tools I've been using to do SFT and RL training. So this is kind of probably an information dense talk, and I might gloss over a lot of details, so happy to answer questions if there are any about this topic. So let me start from the first part, which is deconstructing the term agent. So I think lots of us tend to ask the question, what is an agent? And there are a lot of different definitions that have been provided in different settings by different model provider. We have OpenAI, Anthropic, AWS, IBM. This definition all kind of goes into the idea of having systems that can use LLMs and tools to do things, and so on and so forth. The definition is never very precise because it's better in this context to use a very generic definition that can put together many different systems, but this is sometimes a problem. For more historical context, I have this quote here. The problem is that although the term is widely used, it defies attempt to produce a single universally accepted definition. This needs not to be a problem. After all, if many people are successfully developing interesting and useful applications, this is not bad. So this quote points out the fact that we don't have an actual definition, but that's not a problem because we can still build stuff even if the definition is not clear. However, there is also the danger that unless the issue is discussed, agent might become a noise term and is subject to both abuse and actual misuse. So it's a good idea to open a discussion on the definition and try to find the actual definition of agent. And the funny thing is that this is a quote from 1994. So the problem around the definition of agent has been quite a very long problem that is very hard to solve. And there is also like a very interesting TechCrunch article about the actual definition of agent. If you talk with people that build agents, it's not super clear what building agent means. You could be writing prompt and connect API calls. You could be using different frameworks. You could be creating workflows one after the other. You could be even training using SFT or do training using reinforcement learning. Or you can also do all of the above together. This is not a prescriptive take on any of these approaches. It's just more a descriptive kind of characteristic of what I think building agent could mean. And I think this matters because like, it's hard to evaluate claims generally when you have agents that are not precisely defined. It's very hard to replicate. Like, we don't know if agent A is better with respect to agent B because of very specific components. And it kind of sometimes looks like more alchemy and not science. So we won't solve this today, so I'm not going to provide a definition of agent. I think it's very hard to define agents in this context. What I'm going to do is I'm going to break down these in the most important components, and then we can build up from the most important components on top of that. So if you look at most agents today, these are basically based on the same 8-line loop that you can express in Python. So this is the loop. Oh, sorry, I skipped one slide. This is the loop. You tend to have a user input coming, which is going to be your message from the user, and user, for example, asking a question. You then call the LLM. The LLM is going to return an output to you, and it's going to give you a set of tool calls. If you find that there are tool calls to execute, you are going to execute these tool calls. You're going to basically have a new message, and you're going to start the loop again. You're going to keep looping until you don't have more tool calls to do, and eventually either you ask a new question to the user or basically like interrupt the entire process. This is how most agent systems actually work. Even multi-agent systems are a variation of this context, and it shows how simple the actual general paradigm of creating agent is. The key is basically in the actual implementation. The LLM and the tools are the two most important components, of course, to take into account when you want to build this type of agents. So the two building blocks we are going to start our breaking down the definition of agents are LLMs. So we have output tokens given an input prompt, and is the most simple definition of LLM. And finally, tools, which are something that execute actions outside the LLM. This could be search action, this could be coding action, any tool that you can think of. The missing piece that put tools and LLMs together is parsing. So we parse an LLM response, we interpret this response as an action, and we execute the action. So we start from something that the LLM generates. Assume, for example, the user is asking a question. The model starts outputting thinking tokens. Then it's going to start outputting a set of tool tokens. We're going to recognize the end of the tool request. We're going to parse that out. We're going to execute that, and we're going to feed back stuff to the LLM. This is how, in general, this would work. So the example with the search could be this one. What's the weather in New York City? The LLM might say, with a very specific format, to use search weather in New York City. And we're going to parse this out. We're going to execute a tool, and we're going to return a result. The same goes for code execution. For code execution, we are going to have a data science kind of task. The LLM is going to generate some code for us. We're going to parse this. We're going to execute, and we're going to return some default results. So this is the general framework of how most agents do work, and it's mostly based on parsing stuff that comes out from the language model. This would look something like this. So user could ask, what's the capital of France and its population? So we have the agent that might start thinking, so I need to search information about Paris. It's going to come out with a set of tokens. It's going to come out with a set of tokens for the tool call. We're going to parse this out. We're going to execute. We're going to wait for the result. We're going to feed back the results to the LLM. And finally, the LLM is going to output an answer for us. One thing I want to mention is the difference between agents and workflows. I know that like a lot of people focus on these definitions, so I want to mention this. In general, agent, we use the term agent when we basically have the LLM getting in output every time the feedback it gets. So basically, the LLM is going to decide the next steps autonomously, or you have workflow that defines path ahead of time. As an example of workflow, here I have the OpenDeep research we released a couple of months ago, in which we have a research topic in input. We have a first language model that generates a planning. The planning is a set of queries, for example, to search to find a research topic. We run the search queries in parallel. We aggregate the different information. We use another LLM call to basically evaluate if we found enough information. If we did not, we go back, update queries, and run search again until we have finished this loop and we can write a final report. So what I think the main difference between agents and workflows to me is the design space you want to give to the agent. So either you want to give to the agent infinite options to operate and use the tools, or you want to define some explicit path that the agent has to follow to complete some task. This is my interpretation of how I think about this setup. So how do we go from LLMs and tools to AI agents? So we have the LLM that generates text. We parse, interpret action, tool execute outside the LLM. And finally, we feed the results back to LLMs, or don't if we have done the task or if we have some kind of workflow system. And this is going to be somehow the working model for all the different things I'm going to show today. So the 3 ways to build agents that I'm going to somehow go over today are, the first one is going to be a React agent that is going to use reasoning and acting to do some tasks in the context of data science. So this is going to be a first scaffolding with some prompting. And then I'm going to show some supervised fine-tuning example in which we learn from examples that are distilled from a larger model. And finally, I'm going to focus on some reinforcement learning to show how we can go on and learn more complex behavior by using rewards as a way of learning this complex behavior without basically distilling from another model or from humans. So let me start from building with React, and how do we go from parsing to actions. We need 3 things. We need an LLM that can generate structured actions. We need a reliable way to parse those actions. And we need a safe environment to execute those actions. These are the 3 elements we need to build our first agent. So the first part is going to be instruction following and parsing. So we need a good model that can generate that can follow instruction well so that we can generate our outputs. So remember, we have LLM, text in, text out. We need, from that side, we're going to have this setup in which the LLM basically is going to execute the tool. But what actually is going to happen behind the scenes is that the LLM is going to generate some text. We are going to parse it, and then we're going to execute. So we ask the LLM to generate structured outputs from us. So I have a very quick demo about this. The idea could be as follows. So I could ask this agent to open the file.csv file and show me the columns. Data set. Let's see if this works. So let me see. The agent might generate some instruction, but we need to find a way to parse this. So what we're going to do is we're going to ask the model to wrap the content in code and code docs. Let's see. So the model is now going to generate, hopefully, the new answer. What should happen, and if the model is, now, the idea is that I have a parser behind the scene that is going to extract the content behind the code, the 2 code tags, and is going to give us the Python code that then we can actually execute. This is the video in case the demo broke, but it didn't, so that's good. How do we do this reliably? So what we're going to use is the React framework, which was a paper that came out 2-3 years ago. I think the published version is 3 years ago. And the general idea was we need to build an agent that follows this cyclical process. So it's going to reason about the possible actions it can take. It's going to act, basically defining an action that we can execute. We are going to execute the action, get the observation, give it back to the actual agent, and do this in a repeat session until we get the answer. So focusing on one of the examples I had before, what is the weather in New York City? New York City, we are going to reason, I need to use the weather API to find the New York City weather. Then there is going to be parse the instruction. We're going to get an observation, and we're going to loop back until we are done. While at the agent reason is a very important part of this question, I'm sure that most of you have have experience with probably with reasoning models. And the idea is that like chain of thought or any ways of allow model to think out loud or use more tokens before acting is a very good way to increase the performance in different settings. So basically, like the reasoning is going to be a preparation step for the process. We do the reasoning, we do the action, and we finally get the final observation. And this is how this model are going to behave. So this could be the first system prompt we have. So please reason step by step within think and think tags before taking an action. After your reasoning, specify your action using the appropriate tool tags. So now we have a model that can think. We need to define a way to express actions in a structured way, like we saw before. So what we're going to use is what is called the correct approach, in which we are going to express operations or actions as Python code. Basically, instead of using standard function calls, everything is going to be Python code that can be executed directly. The idea is that like having Python instead of standard function calling gives you a more flexible way of combining tool calls, because you can use the expressivity of a programming language like Python to combine operation, and the agent can use if-elsing or can use any other Python construct to run operations. So as an example, if you had a request like this one, find the cheapest country to buy smartphone X, what you would see a traditional language model do would be something like having multiple call tool in parallel or sequential, where we basically wait each time for the result. What you would do with a correct framework is that like the agent might write a loop to get to the actual answer in one single token generation step. More explicitly, this is what would happen in the context of standard tool calling. So for each country, you would basically repeat this cycle. You would first get a tool call, for example, here, to get the rates for the country Germany, and you would wait the response. You would get the price for a very specific object, and then you would convert this in another tool call. And you would need to do this for all the different countries. You could simplify this a little bit by doing parallel tool calls, but in general, the fact that like these tool calls depend one on the other makes it so that we need to wait for the response from one to get the actual answer of the entire system. But actually, can be very easily expressed with Python. You can basically define the countries. You have a for loop over your countries, and what were your tool calls here? They define functions that your Python agent can use, because these are going to be defined inside your environment, and the agent can just use this as a standard way of expressing.
Can't you just use this as your tool? Like, why do you need the LLM to generate this every time? Because that might not be the most reliable thing.
This is going to be the, can you make it a little more clear? This is your tool in general. So basically, these are going to be your tools. And you're going to execute this code inside a Python environment.
Yeah, but I'm saying, like, this whole thing could be your tool, like, right? That could be the function about.
Oh yeah, definitely.
So why do this, like, have it generate the code in general versus having like your codes set? Because that's going to be a more reliable, deterministic thing, right?
Yeah, so I guess like the balance is going to be of how accurate you can generate this code versus how confident is your model in generating very specific tool calls. In general, models are pretty good at generating code. So for simple tasks in this context, it's easier for a model to do this. Think of, for example, of a data scientist in which like you need to generate tons of code. Doing this with tool calls is a little bit more complex. But yeah, there is of course a trade-off between how your model has been trained if you want to fine-tune it on very specific tool calls. In general, I would say that like the more specific your task is, the better might be to have standard tool calls, because like those are definitely a bit more reliable. In this context, it makes it easier for a general language model because those have seen tons of code. I guess like in the recent couple of years, the tool calling has become much better in the sense that like this has picked up and is basically similar to this system. This is just like because I guess like until a couple of years ago, most models had seen more code than actual tool calls. So this was just a better mechanism, of course. And this was another paper that was published last year at ICML 2024. So here we run one code execution that is going to handle everything for us. So How are we going to structure it? We're going to structure it here in two ways. So we're going to have a think tag to let the model think so that it can generate correct actions. And then we're going to have a code tag to express these actions. So this is what the system prompt might look a bit like. So we're going to use think and think tags to reason about the task. And we're going to use code and code tags to write Python code that will be executed. And here I have an example of a few short example that you could give to your model. I need to calculate the sum of numbers from 1 to 100. And here is going to do some operation. So one thing I want to point out, and like this connects to what I was saying, what I was replying to when I was replying to the question. The important thing is the explicit environment definition here. It could be Python function. It could be very specific tool calls with XML tags. The important thing is like once you define this behavior, you define an explicit way for your agents to behave. And it could be Python function. It could be XML tags, search queries to define how to interact in an environment. And in fact, we are going to see this when we do SFT and reinforcement learning in the next part. But the general idea is once you define this explicit environment, the agent can act. And as long as you can parse out the information, you will be able to execute things. So, OK, now we have code. What can we do? So the problem with code is that like we need to find a way to safely execute the code. There is a safety problem, of course. You never know what an LLM is going to output. The LLM might generate code like removal of your entire disk. And this has happened in the past. Like we saw a situation in which this thing happened. And if you use coding agents, sometimes they tend to delete stuff they should not touch. Oh, yeah. Yeah, so like these are some of the problems that you can get into. And this is why you generally want to have either like a safely backups of your data, or you want to run some of these things inside an environment. There are a few ways to do this. You could use Firecracker VMMs. You can use Docker containers. You can use code interpreters. There are quite a few code interpreters out there now. One, for example, is Together Code Interpreter. That is the one I'm going to use. In general, let's say that like the important thing is that we need to have isolated environment on which we need the code to run. So as an example, I'm going to mention Together Code Interpreter, which is this product that Together offers that allows you to get in real time a sandboxed Python environment that you can just run Python in. It comes with some pre-installed libraries for data science. It can give you like dynamic package installation. It also gives you the possibility of generating images on the cloud and get basically the plot locally. As an example of code, here you would have like importing the Together library. There is a few lines of code to generate this chart. You would just run the code interpreter, and you would get some information outside. Basically, this is going to behave as a Jupyter notebook. So basically, it's going to give you a session ID. You're going to have a session open. You're going to run all the code execution you want, and it's going to give you back the results of your code execution, which makes it perfect to write like a code act agent like the one we are writing basically now. It gives you this flexibility of running all the operations you want. So putting it all together, React plus code act. So we have a reasoning part in which the agent is going to think using the think tag. We have a code action to generate code. We are going to execute the code in a safe box. We're going to observe the result and return them to the agent. And we're going to repeat this in a loop. So this is going to be the full pattern. So we will have the structured reasoning with code execution. The key elements are going to be thinking, code, and the observe loop. We're going to have a structure that is done by the XML tags for explicit formatting. And basically, we're going to have reasoning, acting, and observation. And I'm going to show an example of like answering this question with one of the agents. So compute average sale performance for the last month. This is the question. The execution would look something like this. So the agent would probably start thinking about the question. So to compute the average sales performance for last month, I need to first understand what data is available. So the agent has to basically open the data, look at like what's data inside, and then it's going to I need to scroll down here. So it's going to find some files. It's going to open the file with Python. We're going to execute this on a cloud environment. It's going to look at the whatever amount of data there is. And then it's going to try to compute some information to answer the question, and finally it's going to come up with an answer for us. So the full example here is basically combining the steps the different processes we've been going over in the last few minutes. So thinking step, code step, and then an answer.
What's the data transfer to the code execution?
Yeah, so I'm gonna show the implementation later. We have two ways. One, we have a Docker environment in which basically we mount the local folder. So we mount the local folder inside the Docker container, and we just execute inside the container. TCI can upload stuff for you on the VM. So basically, Together Code Interpreter has a method that allows you to basically take whatever you have on disk, and it's going to upload online for you, and then it's going to execute online.
It has to be done by developers now. It has to be done by us.
Yes. So this. Yes. The alternative is that like you need to explain to the agent how to use the Together Code Interpreter, and then it should be able to do that on its own as long as you give it the documentation. That's the alternative. So it should be able to learn that it can upload the data online. But in this context, in the data scientist we implemented, we basically do this behind the scene. So before running the agent, we upload the data on a TCI virtual machine, so the agent is going to already find the data online. So the nice thing is like the core logic of this is incredibly simple. We might have a maximum number of iterations. We can parse the response from the model and get like some thought and some code. We can check if we are at the final answer of the process. We're going to run the executor online with a session ID to keep our session active. And basically, we are going to append stuff to the history to keep the conversation with the agent going. The setup of this is very easy. Eventually, your agent is going to be no more than 100 lines of code, considering even the call to the interpreter and the system prompt. So it's a very easy way to implement a very simple agent that works very well on a couple of tasks. So I'm going to show an example of end-to-end implementation of this, which is going to be the Open Data Scientist we released 2 months ago, which is basically a full end-to-end implementation of this framework with evaluation and so on and so forth. So the idea was we wanted to somehow come up with a data scientist that was using the React and Conduct pattern, and it could be able to analyze data from start to finish, write Python code, self-correct itself when encountering some errors, for which using the React framework is very useful for, and that could produce some complete research reports. Here is let me start this. I can start this a bit. So this is like a video demo of the agent. So you see now I'm running the agent, is going to do execution with TCI. Before running, is going to find local files, and it's going to upload them on the TCI virtual machine. It's going to come up with a couple of options for you. Here we use DeepSeek V3 as a model. Everything I'm going to show today is based on open source models and is completely open source. That is also, I think, another good point. You can build a lot of stuff with open source nowadays, and even DeepSeek models, or the Kimi models, are now very good and can do these tasks very efficiently. So here I am gonna upload the data. Let me go ahead a little bit. So here, basically, we are asking, let me remove this. We are asking the agent to do some task in chemical engineering. The agent is gonna start thinking. What is happening here is that we are asking the language model to come up with the think instruction and with the code instruction, and the agent is gonna first, let me stop this so I can comment a portion of this. The agent is gonna start thinking. So before computing any correlation, I need to verify that we have a data set. So it's gonna look at the local files. Once it has looked into the local files, it's gonna start and look at the actual columns and whatever there is inside this data. And once it has the data, it's going to compute. It's going to look at missing values as a first thing. It didn't find any missing value, so it's going to go ahead. And then I think the last part is going to simply execute the final answer, which is computing the correlation. And you see that it comes with a final answer that is about the correlation of the data that we were looking at. I need to do this manually now. OK, so it comes with a command line interface. It can write a report. It's a very simple application. I think like the main component is 100 lines of code. It's very easy to use, break, and modify, and it's online. This is a very interesting task. So I had a friend that is a PhD in chemical engineering that tried to ask a question about molecular solubility, and it gave one of his data set that he has used during his PhD. And the fun thing that like the agent came up with like a complete report about this data with plots and everything, which is a pretty interesting application of how models nowadays can actually toggle some tasks that are that were in the past that in the past somehow required a lot of manual work.
So did the model do better than your friend?
Good question. So he said his PhD was useless, but I think he was joking. I think the answer is no. It's not better than my friend, but this is an incredible head start. Like, this is gonna write tons of code for you. The good thing about this kind of system is that like eventually you can extract a Jupyter notebook that you can look yourself.
Yeah.
So it can do everything, and then like there is a component of like you need to verify whatever the agent is doing because it might come up with like hallucinated result. But it gives you a pretty good starting point. Yeah. This is also my take on coding agent like Cursor and Cloud Code. They are not perfect, but they give you like the scaffold for everything in a few seconds, and then you just need to check that everything makes sense. But this is the same.
Does fine-tuning model with certain domain-specific examples would make it better?
Yes, definitely. Like you could fine-tune a data scientist for this. It's a very expensive process. I'm gonna mention some of these later, but since you need to interact with an environment when you, for example, collect data for fine-tuning an agent to do these kind of tasks, you need to collect the real data, which means that like you need to have access to many environments that run Python. It means that like you will have an agent generating some code, you will need to execute the code, get it back, and then you will need to collect the trajectories. This is called rejection sampling, so you basically are gonna collect tons of trajectories, and it takes a lot of time because like your environment is very slow. Like you already know that like language models are slow in general, like it takes time to get output. If you add the component like you need to interact with an environment, getting the data is gonna be a very expensive operation. But yes, definitely, you could totally do this with a real environment. So this is the data scientist structure we use. So it has some rules, the guidelines we give, and the execution tips we give. This is the prompt. So what we do is that like we define some critical rules for the agent. We say you are an expert data scientist. You follow the React framework. You execute one action at a time. The most important thing we give to the agent is the option to take two possible actions. One is basically thinking and writing code, and the second one is providing an answer. So I have, hopefully, a live demo that works. So I'm going to ask the agent to load this data and give me the correlation between the two first columns. So hopefully this is going to run. What's going to happen here is that like it's similar to what I showed before. It's just like this has the complete loop end-to-end. So the results are gonna feed back into the agent. So the first thing the agent is doing is thinking. So I need to load the data file that was given to me. I need to, and basically this is what the agent has generated. So it generated code to basically extract the data from the URL. The second thinking is going to be, now I can see the data structure. The first two columns are MPG and cylinders. Let me calculate the correlation. So what it's going to do is going to try to get the data. It's going to run the correlation, which is this operation here. Oh, it also checked for missing values in the column before running the correlation, and eventually gave a final analysis, final result with all the information. So I need to, again, do this. The actual code to do this is, again, very simple. You need to have some parsing action. You need to have a run agent operation that gets an input a question. This is going to have a system prompt. You're going to have a maximum number of turns that are these ones. You're going to call the LLM with some history and get a response. You are going to save the response from the model. You're going to parse the response, so get thinking and code out. You're gonna, in this context, execute the code on an online environment, and you're gonna add this back to the model. And eventually, if you find that there is an answer, you're going to break the process. So this can be done in very few lines of code in general. Yeah, this was the demo that I'm going to skip. So what this kind of agent that is very simple shows is some very interesting capabilities of learning and adapting and correcting its own behavior. I have a couple of examples of this. We use this to train some BERT models, so to fine-tune BERT models. And we were playing with a Kaggle challenge. And here is, unfortunately, very small, but I can narrate this. So the agent was playing with the BERT tokenizer and realized that it was using, the data we were using had more tokens than what BERT can allow. So it was using the data has more than 900 tokens, and BERT maximum accept 500 tokens. So the agent decides to adapt and decided, for example, here to truncate the data to ensure that we could train this model. Another example of this is an sklearn convergence warning. So we were training very simple models, and the sklearn somehow outputted some warning to standard out, basically specifying that the maximum iteration the agent set wasn't enough to basically correct to basically get a good trained model. The agent realized that this was a problem and basically came out with a new model that had additional maximum iteration to basically address this problem. And another very nice thing is the agent adopting new strategies by opening and looking at the data. So for example, in this context, the agent looked at a data set for toxicity classification that had 6 labels. And the first thing the agent did was looking at the distribution of the labels to understand if it had to adopt some weighting scheme to better perform in any model that you would have implemented. So it showed a bit of the capabilities that this simple system of thinking and then acting can learn. So a few key takeaways for this. The React pattern seems to work very well. With Codact, we can basically do very complex tasks in Python, like writing reports or solving complex problems. Self-correction is pretty critical because it allows the model to perform much better on many tasks. And it's a very interesting behavior to see for yourself when you interact with this kind of agents. So let me go a little bit more in detail with the evaluation because I think it's important in this context. So we try to evaluate our data scientists using a few different data sets. We wanted to use real-world benchmarks. We wanted to have somehow diverse type of tasks. We wanted some data analysis, but we also wanted some ML training capabilities. And we wanted some quantitative metrics that we could get out from the agent. So we basically focus on 2 benchmarks. One is Dubstep, which is a benchmark from Hugging Face with 450 business questions that require some complex data analytics. They don't require training any models, but they require you to understand the data, which is one of the most important parts in data science. And then we use some Kaggle benchmark from the ML bench from OpenAI. We extracted 2 classification tasks and tried to see if our agent could come up with submissions that could be submitted to Kaggle. So this is Dubstep. This is the work. It was released early this year. It's a very nice data set. I would recommend everyone to look at this if people are interested. I think it's very nice because the setup to actually run this benchmark is minimal. Lots of data science benchmark require you to install tons of things, download data from Hugging Face, download data from Drive. This is very simple. It's 5 files with some data inside and very complex questions that are not obvious to answer. So I think this is an incredibly good benchmark to use for this kind of tasks. It requires multi-step reasoning. It has some domain-specific definition and formulas and documentation dependency for success. This means that what Dubstep gives you is a manual, a documentation that the agent has to read. And if it doesn't read the documentation, it's probably going to get the wrong answer. Because in this data, for example, terms like fees have very specific definition that are very domain-specific. And if the agent is going to use its prior knowledge from the pre-training, it's going to fail at actually answering the question, which is a very interesting benchmark because it forces agents to actually read the documentation before acting. And yeah, this is the reason why I like Dubstep. So this is an example of a question. So looking at the year 2023 and the merchant golf club, if we were to move the fraudulent transaction towards a different authorization characteristic indicator by incentivizing shoppers to use a different payment interactions, what would be the preferred choice considering the lowest possible fees? And again, this is a kind of a very complex question in the sense that like there are very domain-specific terms that unless you read the documentation, you might not get the right definition, and this means that you're gonna get the wrong answer. This is the prompt we use for dubstep. I'm just putting it here to show a couple of things. So these are the files that the challenge is gonna give you, and it basically contains most of the information that you need to solve a task. They give you some answer guidelines. They give you, of course, the question, but then we add some additional details to ensure that the agent get the answer right. So the idea is that like we tell the agent to actually look at the manual in detail before answering the question. And if you don't do this, the performance of the agent drops significantly. So just to show some of the results, in general, the Open Data Scientist was at the time of release a pretty good model, a pretty good agent. It was very good on the easy task, and it was competitive with the best models on these tasks. It was very good. It outperformed the Gemini data scientist agent. This is the plot, and I'm gonna focus on this bit. So on the easy task, our model was the best. Our agent was the best one, and on the hard task, it was very competitive. If you look like it's very competitive with GPT 4.1 as a React baseline. So it was decently good, and at the time, this was the only fully open source implementation. So open source code, open source models, and it could run eventually everything on your own laptop. So it was I think it was a decent, good enough agent for this. Mm-hmm. No, on the hard task, we are the third one in the benchmark. So it's this one.
What is the second one? Second one?
The second one, this one, is another agent that is present on the dubstep leaderboard. It's a closed source agent, so we don't know what it is.
Data scientist is also closed?
Yes. So the two baselines are open in the sense that these are Hugging Face implementation of a baseline using their small agent package. The data scientist, I think, is an external baseline that they used. So just to mention how this challenge works, to give more context, you are given 450 tasks. You don't have the answers to those tasks. You need to submit the trajectories and the answer, and you're gonna go on the validated leaderboard. And you just need to basically share the results, your results to the answer with the organizers. So there is no way to get validation without passing through the actual challenge organizers. So this is also why many of these are closed source solutions. It means that like people have run their own agent, and then they share the actual result with the organizer, and the organizer put these on the actual leaderboard. Okay, the other test we did was on the Kaggle benchmark. This is MLE Bench, is a benchmark released late last year from OpenAI. It contains a few ML challenges based on Kaggle, and we extracted two tasks that are based on this Kaggle competition. We use the spooky author identification and the jigsaw toxic comment detection. The setup is similar. We have high-level prompt, we have a discovery task, and we have an end-to-end solution that is generated. So this is an example. This is like Wikipedia toxicity comment classification. You have 6 toxicity types, and it's basically a multi-label classification task that we ask the agent to solve. So the agent has to basically analyze the CSV files. It needs to handle any kind of preprocessing a complex interaction, and has to build a model for the 6 categories and generate a submission file. So this is important. We don't give any specific instruction. We ask the agent to go through the data, look at the actual Kaggle submission, learn what it has to do by looking at the description, and come up with a final answer for this. So we ask the agent to generate a submission file. We pick this out, and we put this inside Kaggle, and we get a benchmark code in return. So eventually what we found is that like the agent gets to a successful result, but the performance is good, but actually not great. It feels like that if you don't prompt the agent is often going to use the simplest solution to solve a task. And in this context, it mostly used TF-IDF plus a logistic regression, which is reasonable baseline, good, and like gets you a submission on Kaggle, but it was never a very good submission. So there is, of course, some kind of space to improve the model by using more prompting techniques. So if you prompt the model to use a BERT, if you prompt the agent to use BERT as a model, it's going to do that. But you need to tell the agent. At least in this context, the agent always assumed that the best solution to approach a challenge was using TF-IDF and logistic regression.
Why is that?
I have no idea. I think most of the data out there is basically using TF-IDF and logistic regression. If you think about it, BERT is like 2019, and the most recent models have at most a couple of years. Also, most data on Kaggle is often for beginners. So there is kind of like, I'm sure there is like it's a kind of a distribution in which you have a lot of like very simple notebooks that contain very simple techniques that gets you to the answer. And those are also the most successful one in a sense that like it's much easier to give you a good submission with TF-IDF than with a BERT tuning. So I think it's probably a frequency issue. And it might be that the next generation of the model as a first thing is gonna start using BERT as a.
Retraining as the bias or.
I assume that could be the case for Kaggle challenges. Also, like, TF-IDF is a reasonable first approach to solve a Kaggle challenge. Like, it's not wrong. It's just not the best one. So I wouldn't say that like the agent is wrong in using TF-IDF. It's just like the process. The process of using TF-IDF is not going to give you the best possible submission. So as a summary of the evaluation in this context, so dubstep give you strong performance on dubstep we saw strong performance on domain-specific task. On Kaggle, we had some end-to-end success, but there's room for better model selection. And the key learning here was like prompt methods and documentation reading and domain guidance improve the results. The future work for this would have been to focus on better prompt strategies for modern ML techniques. So this is like the links to the Open Data Scientist and the blog post. You can run this. Everything runs locally as long as like you put your models and so on. And next part is teaching agents some behavior with some supervised fine-tuning. I don't know if there is any question on this. If not, I'm going to go directly to the next part. Cool. The second part of this talk is going to be on teaching agent new behaviors. And we're going to focus on learning to search and reason to solve search tasks. So before we begin, this is kind of a proof of concept. I'm going to, like I said, gloss over on a lot of details about evaluation. I'm not going to do much hyperparameter selection. I am choosing very biased data set to do evaluation, and the comparisons are not end-to-end. It's mainly mostly to give you a sense of like the end-to-end process of training with SFT and with RL as a benchmark. So what we have so far is this. So we have some scaffolding that we built with the React and the Kodak framework. So that's structured prompt. It can do some parsing. It can do some tool execution. It's working. It is an open data scientist with some self-correction capabilities. But what if we want to model to learn this behavior or learn new behaviors? So in this context, most of what we're doing was done by prompting the model to behave in a way we wanted. What if instead we want to basically tune a model using SFT or using reinforcement learning to follow some very specific instructions? So the behavior we're going to try to teach to a model is going to be to search and to reason about some results. And what we eventually want our model to be able to do is answer a question like, when did the director of Inception win their first Oscar? So this requires searching for a director, searching for Oscar history, and synthesize the answer. We're going to basically work our way from a large model. We're going to sample example from that, and we're going to fine-tune a small model. The two approaches to do this are going to be learning using example from SFT. So we're going to basically sample samples from a large model. And the other one is going to try to use RL to optimize for correctness of the answers. So the pipeline that I'm going to show is going to look a little bit like this. We have a data generation part. So we're going to create the data from a teacher model. We're going to do SFT on a small model using data from the teacher model. We are going to try to train a model using an RL environment, using real-world search interaction. And finally, we're going to basically use gRPO to train this RL model and do some evaluation, of course, to ensure that the results are actually meaningful. So let's start from the first part. Let's start from supervised fine-tuning for agents. So basically, we're going to teach model new behavior. So what do we want to build is something that looks like this. Given an input question from a user, when did the first Star Wars movie come out, we want basically an agent to output a trajectory in which we can see some think token, we can see some search tokens, and we can see some answer tokens. This is going to be the entire process. This is going to be the tool calls. And in between the search and the answer, there is going to be some feedback coming from the environment. So this is the thing we want to build, and we basically need data in this exact format. So we need an entire example, so input-output pairs to train on, but that also contain the entire trajectory to do SFT. We need also the search answer inside the system. So what we're going to do is that we're going to do a larger model to fine-tune a smaller one. As a very quick summary or introduction to how LLMs are trained, in most contexts, training LLMs means increasing the probability of some text completion. This is true for most technique. It's true for pre-training. It's true for supervised fine-tuning. It's also true for reinforcement learning. There are some differences in the details, but in general, this is kind of a true assumption. Any kind of training method is going to try to improve the likelihood that you generate some very specific tokens. What's going to change is how you are going to try to make that happen. And so basically, given this input, you would want to increase the probability of this generation. What we do with supervised fine-tuning in general is that we want to train a model on example of desired behavior. And in this context, the desired behavior we want is that we're going to go from input, like this question, to output, like this one, using the search tags we want to need. So where do we find the data to do this? One way could be focus on humans, for example. We could collect data from humans, but that's very expensive. So what we're going to do is that we're going to distill information from a large model. We're going to use rejection sampling as a technique to do this, which is a very classical technique to collect data from larger models. Sorry. I think there is one slide that is not going down as it should. Anyway. Let me skip this. So the idea of knowledge distillation is that we want to generate many trajectories from a teacher model, and we're only going to keep the correct ones. So we will ask a larger model, which is going to be a Quen, one of the large Quen instruction 2 models to generate trajectories from us. And we are going to only keep the trajectories that have a correct answer, and we are going to throw away everything else. So this is going to allow us to create a big data set of correct trajectories that contain think, search, and answer. So what was going to look like, it's going to look like a little bit like this. So when did the first Star Wars movie came out? And we're going to have from the model some answer. We're going to keep this one for obtaining. We're going to discard the bad answer, for example, this answer that has the wrong answer. We're going to keep also this one. So we're going to do this process for all the questions, and we're going to generate a data set of correct answers. And we're going to train only on the correct trajectories. Our distillation stack will look a little bit like this. So we're going to use TogetherAI for the model sampling, Tavily for search, and Quen agent as a scaffold to actually sample the trajectories. So TogetherAI will offer the teacher model we're going to sample from. Tavily is going to be our search API we're going to use to interact with the environment. And finally, we're using Quen agent as the scaffold, which is one of the most important parts of this data extraction process. So we're going to start with the teacher model. We're going to use this. This is one of the latest Quen model, and it's the one that is only instruction tuned. It's not a reasoning model. I'm using this because it's just easier to get the outputs from this model without waiting for the model to wait to think. And what we're going to use as a student model is the Quen free 4B model. So this is the small model we're going to fine tune on the data. As an example, this would be the API call you would use to get data from TogetherAI model. It's simply like you just give the input model and then you sample data from it. Tavily is the main component of the search. I'm using this because I think it's a very nice API that you can easily wrap inside a tool. Once you have an API key, you just need to use their client, do search, and you're going to get an answer from the environment. So it's very easy to implement. The most important component here is going to be the framework we use as a scaffold to extract the trajectories. So QuenAgent is basically a prefabricated agent from the Quen team that you can just initialize with some tools and with some language model from the Quen family. And what it's going to do for you is that it's going to basically run, and it's going to generate it's going to generate the answer for you using the tools. But for us, the important thing is that it's going to give us the actual trajectories we are going to use for training. So we give QuenAgent 3 tools in this context. The tool number 1 is a think tool. So I'm going to tell the model that at the start of each step, it should think on how to answer a question. And it's going to use a think tool to do this. Basically, this is a wrapper tool that we use, and there is a query parameter that the model is going to use to just think. We're going to give, of course, the search API so the model can search. And finally, we're going to give a tool that is called the final answer so that the agent can use this tool to basically notify us that it has found what it thinks the final answer is. So think is going to be used once before taking any action. So it's going to take a think parameter describing the thinking process. Search is just a standard search API we're going to call. And the final answer is something that the model is going to generate. So this is like very simply how you would implement this scaffold with QuenAgent. Once you implement their class and add the tool usage, you just write a loop, and it's going to run everything for you. This is the full example of what we're going to get. So given a question, when did the first Star Wars movie come out, this is going to be what the output is going to look like, more or less. So we're going to have a think call with the think description from the model. We're going to have a search for the search with the parameter. We're going to have some tool response from the agent. And finally, we're going to have a final tool call with the final answer. So we're going to do this a few times, and then we're going to transform this into something we can use to fine-tune the model. So basically, we're going to add this input, and we're going to transform this in this format that is easy for us to play with without the entire tool calling system. One thing to notice is that, and I'm going to mention this again later, when we fine-tune this, we need to mask the output in the loss, because otherwise the model is going to learn to predict the tool tokens, the tool output tokens, which is something we don't want. So when you fine-tune, generally most frameworks do this for you, but since in this context we have a custom format, in the loss I had to mask the tokens of this part. This is just like a minor implementation detail. So which data do we use to start the distillation process? So I'm using this dataset from Google, which is called Natural Questions, which are real queries on Google. It's a dataset from 2018, if I remember well. These are basically human verified questions. It contains a lot of data. An example of question could be this one. So in Greek mythology, was the goddess of spring growth? And the answer is Persephone. So we are going to use this data as a way to sample from the big model. What we do is that we sample 4 times for each question and discard the bad examples, getting a total of 400 full samples. This is a very expensive process because we need to sample more times, because due to temperature, some of the answers that the large model might get are wrong, and we need to discard those. So basically, we're going to sample multiple times and we came up with a final data set of 500 full samples. So going more on the fine-tuning, the question is why this should work. So we create an explicit structure for the model to use these tokens, and even if it is a reasonably small model, it should be able to learn this. Oh, it's fine. So the idea is that these rejection sampling process is going to allow us to get better quality over the dataset, because we are going to get only good answer to fine-tune from. And finally, we basically allow the model to learn from the knowledge of a larger model, which is by scale better. I have a couple of training details that I'm going to mention. So basically, our training objective here is to basically learn formatting for the model. I'm starting with the Quen free 4B model. This is the hybrid model from the Quen family. I'm not using the instruction tool model. And I'm doing LoRa fine-tuning using the SFT trainer from Hugging Face. I have a bunch of configuration here. I have a kind of very low learning rate. I'm training this on a full node, so it's hate H100, and it generally takes 5 minutes to train this. I'm just doing a single pass through the data with one epoch. I'm not checking for any validation measure. I'm pretty confident that is enough to not overfit. And couple of other parameters for fine-tuning. This is like the critical part is that we need to do the output masking to avoid the model learn to predict output tokens and hallucinating those output tokens. This is generally very important because otherwise the model will lose a lot of compute to just learn to do this. And eventually what the model is going to learn is going to be able to generate think tags, it's going to generate search tags, and it's going to generate answer tags. And this is the system prompt I'm going to use for both SFT and RL later, so you're an helpful AI assistant, and a general summary of which tokens it is allowed to use, so think tokens, search, output, and answer, and so on. The training code, even in this context, is very minimal. Once you have the data set, you can just use the SFT trainer from Hugging Face. You just define the LoRa config, you just run the training. The only thing that is big and is missing is the custom data collator for the loss tuning, but it's nothing that is too crazy. It's just like an additional output masking collator that I have excluded from this. I'm going to use 2 evaluation datasets to test the performance of this model. I'm going to use Simple QA, which is an OpenAI dataset from a couple of months ago. I'm sampling 30 questions just for testing. It has very short form answer question. For example, who received the IEEE Frank Rosenblatt Award in 2010. And it's a very straightforward dataset with straightforward question. It's generally not used for evaluating search. It's more used for hallucination kind of evaluation in pure language models, but it's been recently become popular in lots of retrieval augmented generation evaluation. So I'm just using this because seems reasonably popular. Also, I'm using a multi-op question answering dataset in which you expect an agent to search multiple times to find the answer. This is another Google research dataset from last year. An example of question is this one. As of August 1, 2024, which country were holders of the FIFA World Cup the last time the UEFA Champions League was won by a club from London, which requires doing some multi-op search because you need to break down this in multiple steps to actually answer the actual question. And the evaluation setup is very easy. Simple QA, I'm using all models with multi-step research. Even the baseline without tuning is initialized with the same prompt, can use the same tools to get to the answer. And the results are interesting in the sense that we see an improvement in performance of Simple QA. The idea is being the model is able to do search and learn to do search. But funnily enough, on a multi-op search, both fail. So we basically train a model that is able to do single-step search, so one-shot RAG kind of system, but it's not able to reason and go through a more complex set of questions. And this is why we're going to bring reinforcement learning in the system. So now we want to go from simply doing SFT to something that is a more complex optimization using rewards. And I have a very high-level introduction on RL for this topic. So the question is, what if now we don't have trajectories from an actual large model? We might have the questions and only the answer, for example, like the frames dataset, but we have no way to sample data from a larger model. And this is where reinforcement learning might come to help us. So the SFT gave us the formatting, so the model can generate think, search, and answer tags, but now we want to generalize this performance so that the agent can, for example, tackle more multi-op kind of questioning task. So what we're going to do is that we're going to use reinforcement learning, and we're going to train a model to find good completions on its own by interacting with an environment. So the agent, which is a language model, is going to generate queries. We're going to get samples in real time of the results, and we're going to feed them back to the actual agent. So very quick summary of GRPO. That is the one I'm going to use to train the models. This is DeepSeek Math, which is the paper that introduced GRPO last year. GRPO became more popular with the DeepSeek R1 paper, in which they showed that they could learn to do reasoning using the GRPO algorithm. But it's a very nice algorithm that allows you to train language models using verifiable rewards, which is the one we have in this context. So the idea is very simple. So for each example, what you do in gRPO is that like you sample completion from a model, you tend to reward complex completion, and the model learns from its own exploration. So there are different RL algorithms, but I think gRPO is generally simple to understand. The complex part is more in the math and the actual infrastructure. So one thing for which RL is very hard is that infra is very complex to deal, because you need to have models that do the sampling while you do the updates to the model. But gRPO is a reasonable, interesting algorithm that I can explain quickly. There are other components to the gRPO loss that I'm not going to mention. The KL penalty, the fact that like you have a clipped function and you need to load a reference model. But the general idea can be summarized with this image. So assume you have a question, you have a policy model, which is your language model. You're going to generate a bunch of observation. Ignore for a second the reference model. You have a reward model, which could be an actual reward model or a function that tells you if an answer is correct or wrong. You are going to get a reward for each of these observations, which are your actual answers. And you have a group computation that is used to create the advantages, which is a way of basically normalizing the output. And what you're going to do is that you're going to use this information to basically update the policy model. This paper here, I would suggest to anyone that is interested to better learn or see the relation between SFT and reinforcement learning. This is a very nice paper to read. It's like it goes not too deep in the math, but it gives you like a very high-level view of how historically we went from a standard SFT system to rejection sampling to PPO with reinforcer to more model gRPO systems. So the key difference between SFT here is that what we're going to do during training time is that we're going to call the Tavily search engine while we train. This means this is very expensive. So it means that like every time the LLM generate a search operation, we're going to call Tavily. We're going to get the result. We're going to get the final answer from the model. And then we're going to reward the model if the answer is correct or wrong. And we're going to do this a bunch of time. And what gRPO does is going to basically compare the different responses and come up with like final update values for the model. One important thing in RL is one of the things that I think is the most fundamental problem of training a model with RL is kind of like the reward sparsity problem. So if your model is not able to generate any correct completion out of the question you give it to, it's never going to learn. So the assumption here is that you need to have a good enough model somehow to start to be able to get some reward from the system. So if your model is not good from the start, it's not going to be able to learn anything. This is why generally you start from an SFT tuned model. So the reward we give to the model originally were this. For example, 1 if the answer were correct, 0 if the answer if the answer was wrong, and no reward during the trajectory because it's gRPO. But like, what did happen when I tried to train a model like this is that like the binary reward was not enough to guide the model to the correct answer. So I had to do what is called sum of reward shaping. So basically I changed a bit the reward, and in my second version of the implementation, I started to give some reward to the model to use when it used search, and penalize the model when it forgot to use search, basically when it was back to a situation in which it was behaving as a standard language model. And this seemed to work reasonably well for this task. There are other solutions to reward sparsity problem. This is reward shaping. You could also do curriculum learning, like you could start with very easy examples so that the agent can get some reward, and then you could complicate the system over time. And you can do worm starting, so initialize with a model that has already some capabilities, which is actually what I'm going to do. I'm going to train the model I've trained in the previous section with SFT, and I'm going to use gRPO training to improve the behavior of this model. So core distinction here between SFT and RL. SFT mainly works on imitation. So we tune the model to match the original input in this context, so copy what basically the teacher did. What we do with gRPO RL is that we have a more exploration approach. So we sample multiple completion, we reward the best one, and we actually penalize the worst one. But it is that the model is searching for the best completion. And this is why GRPO methods are very successful in this context. Again, very important to consider that like if the model cannot find the right completion for any input, the RL model is never going to learn anything. And this is one of the major obstacles to RL. So we still need some data to train this model, and what I'm going to get is a multi-op question answering data set that has no trajectory inside, so we're just going to have the question and the answer. And this data set is music, which is a benchmark from a couple of years ago, multi-op questions. It contains some questions like this. What year saw the creation of the region where the county of Hertfordshire is located, which means that like you need to break down these in multiple searches. The agent has to go through different possible search strategies to find the actual answers. So training the environment, what I'm using is SkyRL, which is a very nice package to train RL models. It kind of takes care of a lot of the infra for you, which is, again, one of the most difficult problems in RL, because like it basically starts the VLLM instance for you. It runs whatever updates you need through the array workers. So it basically allows you to implement everything with few lines of code. Alternatives are, for example, Verl, the Volcano engine reinforcement learning framework. But I like SkyRL. It's pretty simple, and it gives nice abstractions to build agent. So the idea with SkyRL is that like you're just gonna need to implement an environment, which is gonna be something like this. Like you have an environment class, which is gonna contain some actions. So it's gonna basically parse something that comes from the language model. It's gonna check if you are done with the answer. If you are done with the answer, you're gonna compute the reward score. Here you see my reward, which means like if the model has used search, we're gonna reward by 0.1. Otherwise, we're gonna reduce to 0.5. And we're gonna call the Tavil API. We're gonna get the observation, and we're gonna return a final result. This class is associated to all the trajectories you sample for the model, and it makes it very easy to build agent, because like this is a nice abstraction to build this relation between the search and the actual output. So train the agent in practice. I'm using like, yes, the SFT checkpoint. I'm taking 300 questions from the music benchmark. I'm taking 4 samples per question for the group comparisons. I'm training this for like maximum 5 turns, so like the model has to find the answer in 5 turns, otherwise I interrupt the trajectory generation. And there are a few stop tokens that I use to detect when to stop and when to generate the output. The training loop is reasonably simple once implemented. You sample a bunch of 8 questions, generate 8 completion for each task, which means 32 total. You execute the searches, compute the reward, and use GRPO to calculate the advantages. The model here is going to be able to learn to do better search queries, because it is interacting with the environment directly, so it can do operations on top of the environment. And it's going to be able to learn when to do the search and when to actually answer. The idea is that like once you learn to interact with the environment, you should also learn to adapt to the fuzziness of the environment itself. Not all your queries are going to be good queries, and if you make a bad query, the agent is going to be able to learn to recover from its own mistakes. And this is what you expect an agent that interacts with an environment to actually learn. And the idea is that like it's going to basically learn to do multi-op reasoning across the environment. So evaluation and results on this. One thing I want to say, RL is very expensive. If you need to train this, you need to do tons of queries, for example, to the environment, for example, to Tavily. So you need to do samples per batch size, per epochs, interaction with a possible environment. In the context of multi-op search, it means that like each trajectory might do multiple searches. So training this was effectively expensive, because each training run has to use, for example, some credits to run API requests online. But this is part of the problem. When you interact with an actual environment, you need to pay the price of interacting with the environment. Even if you do RL for coding agent, you need somehow to execute the code somewhere. And so that's kind of the expensive part. Unlike SFT, this SFT was much less expensive under this point of view. Once we do the rejection sampling and we generate all our trajectories, we can just use those trajectories to basically do SFT on the model. We don't need to resample anything another time. So as complete pipeline, base model, SFT, RL that is optimize the agent with GRPO, and finally we come up with a final model that can search and reason. Finally, on the results, what I can show is like the agent improves on simple QA, but nicely enough, it also improves on doing multi-op multi-op question answering, which is pretty interesting. It means that like using RL, we were able to basically do some kind of generalization in this context. Again, this is a small model. I didn't expect to get maximum performance for this, but it's interesting how a very straightforward pipeline of SFT with distillation and then some RL with verifiable rewards can give you a model that can already do some multi-op search. And this can be implemented completely in, I guess, 1 day of work, considering like all the good open source tools are there. SFT trainer from Hugging Face, Sky RL from the Sky Lab at Berkeley. So I have an example of this that was fun to look at. So like this is a very complex question from the benchmark in frames. So if my future wife has the same name as the 15th First Lady's mother and surname as the second assassinated president's mother maiden name, what is her name? And so like what I saw that like is the SFT model starts well, but then it gets confused on one of the answer. Instead, what happens is like the RL model is able to basically do everything step by step, can break down the question in the right manner and come up with the actual correct answer, which is really interesting. And there are a bunch of examples like this. Like when you go from SFT to RL, you see the difference, most likely because you are not learning imitation, but it's basically the model learning which are the most likely completion it has to generate to actually come up with the right answer. So key takeaways from these talks. We have basically these two phases. One is SFT, in which I mostly use to learn format, and the second one is RL to do optimization, and the combinations seem effective for this kind of tasks. We found a way to basically do some kind of handling of the sparse rewards using GRPO, and finally, the important part of RL is that we have interaction that matter, and it was able to allow us to train a model that was good enough to do multi-op search without having to collect data from humans or doing distillation. And this is more on the structure of how I trained the model using low learning rate and the KL penalty. So quick summary of today. So we basically covered on we started from the general definition of agents, and we broke everything down on two components, LLM and tools, and we found that the piece to put things together is basically parsing, and we use parsing to build this agent, which is the open data scientist that use reasoning and Kodak to somehow come up with answer. I then show that we can train the models to basically express this behavior natively if we can do distillation from a large model, but also that we can basically use a complete pipeline for distillation, SFT, and reinforcement learning to fine-tune a small model to do, for example, multi-step research. A few key insights. Agents are not magic, but there are some very cool engineering patterns that we can use to understand and reproduce how agent work. Training matters, and we can learn some agentic behavior by fine-tuning and not just using prompting like in the first React agent. And finally, the environment is very important, and defining well rewards and how you interact with the environment is something that is going to make your fine-tuned language models much better. Yeah, thank you.